All right, so I'm glad you guys all made it, and we're very excited because the guinea pigs were before you on Monday and Tuesday, and those were the examiner workshop. We actually ended up making the workshops a little different. Your counterparts that had their Monday and Tuesday class, they had a little more lab time. They fortunately prepped some of the samples already for you, so you won't have as much lab time. And instead, you'll have a little more discussion time that really applies to more kind of manager and technical leader issues. And we'll talk about that a little later on day 2. But you'll still get the same amount of time on the instrument if you're wondering if you're going to get shortchanged. It's mostly the sample prep. So anyhow, welcome, and you are in the laser microdissection class. And why are you here? Most of you are here because you want to separate sperm cells from sperm epithelial mixtures, and that's really what we're concentrating on here. And this image here is just a image of a slide of a mixture of sperm and epithelial cells under the laser microdissection scope. And the picture on the right is actually after the dissection of some sperm and epithelial cells. And the purpose is, of course, to do DNA typing on these samples. So just to introduce ourselves, my name is Christine Sanders, and to give you a little background, I started working for the Los Angeles Police Department in 1991, and I worked there for nearly 11 years in their DNA unit. And so I saw the evolution from just doing the protein and ABO typing all the way through PCR and STRs. And then in about 2002, I moved to Chicago, where my husband was going to medical school. That's why it says Chicago Medical School, now called Rosalind Franklin University of Medicine Science, which is RFUMS. And I decided to get into actually some research, first neuroscience research for a very short period of time because I couldn't seem to get that forensic bug out of my system, I guess. And then at that time, I actually went into forensic research. And we'll go into detail about that later. And so now, though, I live in Pittsburgh, and I'm a full-time mom and a consultant. And what I'm going to do is have the other instructors introduce themselves, both Kelly and Pat. We also have Andy Lee from Leica Microsystems, who knows every single detail about the instrument. So if you have a very detailed technical question or issue, he can answer it. So Kelly, do you want me to come?
Hello, everybody. My name is Kelly Rayleigh, and I currently work at the North Louisiana Criminalistics Laboratory. I've been there for about 4 years, but before I was there, I did work at the Office of the Chief Medical Examiner in New York City at the Department of Forensic Biology. I went there right out of graduate school, and I spent 6 years there. The first 2 years I spent as an actual analyst, examining analyst, and then after that I was a supervising analyst where I did do some casework, but also did technical reviews and duties associated with supervisory duties. So when I came to the lab in Shreveport, I happened to go to the Academy meeting in 2004, and that's where I met Christine, because she had given a presentation on laser microdissection of sperm from epithelial sperm mixtures. And because I had just come from New York City, of course, where there's a large volume of casework, I was like, oh my gosh, this is great. I immediately saw this application. And in Shreveport, at the time, we were still doing organic extractions on, doing the differential lysis. So I said, oh my gosh, this organic thing just takes way too long. We need to do something else. And we had already been at our lab kind of tossing around the idea of doing something different because, of course, sexual assaults make up a large number of our cases. So we kind of tossed it around, and then eventually we decided on validating the LMD. So then, of course, Pat gave me the project, and so it's been sort of a journey from there. But that's sort of how I've ended up here. And hopefully I can share my experiences with you from the crime lab caseworking side, and sort of how I've ended up with the process that we've used or hoping to use in casework with LMD. And it's going to be a little different from Christine's, but hopefully that'll kind of give a little different perspective.
My name is Pat Voitkevitz. I started the North Louisiana Crime Lab a very long time ago. This is my Actually, I'm starting my 31st year. I've been 30 years in forensic science. I started in the days of where a whole rape kit was nothing but a slide to look for sperm. I've done the ABO typing, the polymorphic enzyme typing, and you from California are probably familiar with the Grombong-Raxel wars. I lived through those, of who was going to do this or that or what type of typing. So I've been through just about every amount of DNA typing or regular forensic serology, except for the RFLP. I somehow missed that. But I had the DQ alpha, PMDQA1, D1S80, the initial CTT, triplex, Amplistar blue, green 1, profiler, profiler plus, SGM plus, cofiler, and now we're starting a little bit on identifiler and minifiler. So I can recite just about all the names of all of those. I am the director of the North Louisiana Crime Lab, the headquarters laboratory in Shreveport. There's actually a person above me that's the system director. We have 3 laboratories, of which the Shreveport laboratory is the main laboratory. Over the years, we've had a really good policy of being trying to be innovative, doing new techniques, new procedures, and so forth. And this was just an extension of that. Many of you who've probably been in the 1980s realized how important microscopes were to forensic science. And when I saw this information about the laser microdissection, be able to put the biology and the microscope together again, I thought this would be really important, or really something that's really nice. And as we talk about it later tomorrow, about later in the week, I could have said that earlier, but later tomorrow, we'll see how this is really important. The bringing the microscope back into forensic science, or at least in forensic biology, I think it would make a big contribution to the serological or the forensic biology world. And I think Christine has a few more comments.
All right, and I also want to really encourage questions. Don't feel that you have to wait till the end of each session. We really want to have a lot of discussion. So please feel free to just ask a question at any time. I'm going to try to not focus so much on all the software and things like that. When we're in the lab, I'm going to mostly try to just get you by to be able to cut samples, because this is not a class about how to use the software. A lot of the things we're going to talk about will be actually the downstream work, which hopefully will be helpful for you guys. So you figured out by now, where are you? You're in Largo, Florida, and actually I didn't know where Largo, Florida was when they called me up until I had to look it up on a map. And you're at NFSTC. I put a website there if you wanted to ever find out more about NFSTC. And we're not going to do the walking tour. You were told where the facilities were. The lab is actually in a different building, and you'll kind of get oriented when we walk back there. So just briefly, let me go through what you're going to talk about. And these slides are actually from the first class, so I might add a line in there. Day 1, we're going to talk first just about introduction to microscopy and LMD technology. And also talk, for those who maybe are managers and it's been a long time since you've looked at sperm and epithelial cells, a little bit about basic cell identification. And you are not going to prepare samples for the LMD because the last class did that. I will review, though, how we do it in the laboratory. And you will get a demonstration instruction of the LMD instrumentation. Then you will actually collect samples later this morning that we will have analyzed by the NFSTC staff behind the scenes this afternoon and overnight and the next morning. And then on day 2, we will actually start doing the research studies this afternoon. You'll have lectures in that. And then tomorrow you'll continue with getting lectures in the research studies in forensic LMD development. And you will be actually going back in the lab and looking at some of the advanced applications and how to use the fluorescence capabilities of the LMD. Kelly and Pat will talk about their LMD experiences actually in the forensic laboratory. And then hopefully, knock on wood, if your samples work, we'll be going over the DNA data results. Unfortunately, the first class, it didn't really work, and we were starting to troubleshoot the last couple of days. It's really difficult when you have a new protocol, and all of us are coming from somewhere else, and so we have a brand new lab, instruments in a completely different facility, and protocols that we're not sure if the one little thing got missed out that maybe we missed. And we have a couple of ideas, and when I go in the lab, I'll kind of tell you what the changes we made. Practical application of LMD in the forensic laboratory we'll talk about. And for you guys, we will have some roundtable discussions about some things like validation and courtroom issues, things like that that you may be concerned with. And that's the introduction. So the next part is Pat will come and we'll talk about microscopy and LMD technology.
My talk is basically to kind of bring you up to speed in a brief manner on laser microdissection, microscopy, anything like that, where you can learn a little bit about, at least get some basic information on it. Basic microscopy. I just want to cover a couple of terms of microscopy. I love microscopes. I had my first microscope at 15, and that changed my direction in life thereafter. I got the microscope, looked at paramecium and whatever I could see in pond water, did a project on it in high school, and I knew by that time what I wanted to do with it. Basically microbiology or something like microbiology. So I stayed with the really small stuff, and then I got even smaller down to the proteins, and then eventually down to the DNA from the work that I did. But a couple of terms here which I've seen over the years people kind of misuse, or I don't want to say abuse, but misuse, maybe don't really have complete understanding of, but they still use it. Magnification. This is the apparent increase in size of the object based upon microscope's objective, ocular, and body tube. Those are all things there that affect the size of the object that you're looking at. Magnification is not the same as resolution. You also have to be very careful when you talk about magnification, because you look at the magnification of an object, you say, okay, it's 100x. Well, that's fine. When you blow up on an 8.5 by 11 piece of paper, it's a lot more than 100x. So oftentimes when I'm talking about microscopy, I don't use the magnification I'm looking at. And what you're going to see when you go into this workshop is you're not even going to be looking in the eyepieces anymore. The magnification is that you're reading, okay, is the objective and the ocular, and you say, okay, I'm looking at 100x magnification. But when you're looking at 11 by 14 or whatever size screen, 24-inch square screen up there, it's a lot bigger than 100x. So normally when I'm talking about magnification, I'm only going to use terms like this is the objective I'm using, a 40x objective, a 63x objective, because that really tells the user more information than saying I'm looking at 100x. Refraction. That's how microscopes work. As the light travels from one medium to another, it changes speed, or actually in this case it bends. So refraction is a change in direction or velocity of light as it passes from one medium to another. That's how we make the images. When you look at a microscope, you say, okay, the light went up through it and I see dark areas, and the light is not stopped. These are translucent materials. All the light's being doing is being bent. It's being bent out of the area that you can see it. Illumination, method of applying light to the sample from the light source. I like Köhler illumination. It's a very good method of illuminating stuff or samples. It's a Brightfield method. It gives you good resolution, good consistent materials, good consistent background. I can remember when I started microbiology, we were dealing with all sorts of different. No one really knew ins and outs of the microscope. They just said, well, get a picture up there, see where it looks best. But if you can ever learn to really get good illumination or the right kind of illumination, you can really increase the power or the ability to collect light in your microscope. There's also vertical illumination. We're going to do that. That's when you bring your light from the top. We do that with fluorescence. I know most people, when you come to this class, you say, okay, cut sperm and epithelial cells. Well, we have some really neat new applications where we're doing things besides just cutting the sperm and the epithelial cells. We're now looking at some new stuff, really new stuff on this microscope. I'm going to let you hang for that until tomorrow. So you may have already read about it, but it really is neat, some stuff that you can't even do in forensic science right now. We've got some new techniques out there where we have a whole new capability by using this type of microscope. Here's just a kind of a overview. You've probably all seen this picture where the light goes through there, and you see the different objectives and lenses and stuff like that. And if you remember F's and P's and Q's and stuff like that, we're not going to go into those wonderful formula. Light source is focused through a sample collected by the objective lens and then passed on to the ocular, the eye, the retina. The other part over here is just a very simplified version where you see the light coming through. It hits the object. Now, in most places, what you see, or most books, when you see that hitting the object, you say, okay, well, there it is. It's stopped. It's not actually stopped. That light is actually deflected or refracted. Remember that first definition? Out of the light gathering area of the objective lens. That's why it appears to be a dark area. It's not because that light was stopped. Now, certainly there are some opaque substances, but these cells are not opaque. They're translucent, but what they do is they bend that light to different degrees, and that's why we have other things like phase contrast, differential appearance contrast. Those are other methods of illuminating or visualizing the source, the sample. And it's based upon the ability of these things to refract the light. Specimen refracts the light, which bends it out of the collective area of the objective lens, and that gives you your dark image. The objective lens is probably the most important part of the microscope, because that really defines the resolution of the microscope. You can get inexpensive objective lenses and you will regret that. You may not even know the difference. But once you look at a really nice objective lens, you will see the difference. You'll say, oh, I can't go back there anymore. Objective lenses can be as simple and as what you would go to the store and get your, I think they call it Jason microscopes. That's the one I bought many years ago. I looked at it and said, oh man, this is great. It can magnify 1,200 times. It's great, but the objective is so poor, once you get up about 100x, you can't see anything anyway, all a big blur, or the lens is not, the objective is not flat. There's a number of objectives out there, the apochromats, the planachromats. Those are ones that not only correct for the color aberration, which gives you little bitty fringes around the sample if you don't correct for that, they also correct for a flat field. Older microscopes, the only part was in the focus was just in the center of the microscope. As you move more towards the periphery of the field, it became more out of focus. The planachromats and the achromats correct for that. Or the planachromats correct for both of them. But you also have a new generation of lenses that are really, really bright. They can collect more light. Somehow or another, I think they have coatings on there that can really pull in that light, make them bright. And you don't notice that when you're doing with Brightfield, because you just turn the illuminator up if you need more light. But when you're into fluorescence, you really need some light gathering or light pulling objectives. I say pulling in a sense. They're not pulling it, but they're gathering better of it and making it brighter, less diminution of the impact of the light source. So I really think when you go into fluorescence or the objectives, you really should be important. But there's two things that really affect the resolution. The objective lens is the primary source of resolution. That's why if you take a picture, if you have really good resolution in your objective, you can take a photograph and blow it up much, much larger and not see the difference or see problem. But and the other part is the substage condenser. But in this case, because we have to put tubes in between the substage condenser, we really don't get the benefits of all the resolution there. But if you have just a microscope without the tubes, your substage condenser, but your objective lens does affect, but your objective lens is really the one that gives you your high resolution, your ability to distinguish fine detail. Fluorescence microscopy. In this case, we do this with, most cases you do it with epi-illumination or vertical illumination. Some of the older microscopes actually did go through the sample, through the bottom light. The one we have here does top illumination. This is the illuminate the sample with the UV, 365 nanometers is a common one. What this does is it excites the fluorochromes in there. In other words, it pops an electron up to a higher level, and the electron will spontaneously drop, and it will emit a photon. And this photon, the color of this photon, or the wavelength of this photon is fairly characteristic of that because it can only drop in discrete energy quanta. So again, it illuminates the sample. Here's your fluorescent coming down, illuminating it with incident light to the side. You have, move that out of the way, you have your fluorochromes here, the blue and the red. Fluorochromes are energized and electron moves to a higher energy state. The energetic electron then drops back to the normal state, sometimes call it ground state, releasing an energy photon emission. This goes up the eyepiece here, and then it goes into what you call your bypass filters. Well, there's going to be a lot of that background fluorescence. So what these bypass filters do is, one, they filter out the excitation beam, only allow the emitted colors to come through. In this case, we have a dual bypass filter, which lets both the red and the green come through. You can get single bypass filters that would only let the green come through, or the red, or blue. Or you can get as much as the triple bypass filters that will let all those colors come through. So you can control what you see with these. And it just depends on what filter you want to use in there. The other point, the other terminology would be your resolution. The ability to distinguish 2 points as distinct and separate. Typically your resolution is about 1,000 times the numerical aperture of the lens. So about the maximum, if you look at some of your lenses, objective lenses, you'll see the numerical aperture of the really good ones is above 1, 1.1, 1.2, maybe up to 1.3. So theoretically, you have a theoretical resolution of about 1300x. That's about the most you can blow it up before you really don't start seeing any more detail. What many people do is they will start to try to magnify something or get the high magnification. Like I said, my little Jason microscope can magnify 1,200 times. But it had no numerical aperture on the objective. So what it was doing was simply magnifying it bigger and bigger, but you weren't seeing any more detail. Pretty much like these little bugs on the side here. If you have low resolution, you see this kind of rounded shape. A higher resolution gives you more detail, so now you can start seeing the individual legs of this little, I think it looks like a louse or something like that. If you magnify it too much and still not getting any more detail, that's what's called empty magnification. Basically, magnification has exceeded the useful magnification. And if you see what's happening with this magnification, look down here. Here's the same sample or the same image, much smaller, is magnified less, but you can't see any more detail with it, can you? So magnification really has no bearing or no concept on resolution. Resolution is done through the objective lens. And higher resolution lens will give you a better resolution, or a higher quality lens will give you better resolution. So in that sense, that's why, again, you want to get some higher quality objectives. Now, all of these microscopes are way up in the bucks. So they're almost always going to have good objective lenses. But one thing you want to do, if you go with these microscopes, whatever one you go with, and I really suggest that you go with fluorescence attachments to it, you're going to need not only really high resolution objectives, but good ones that can pull in the light, because the fluorescence is a much dimmer type of illumination. And you're really going to need a good microscope to be able to pull in that light. And there's not a whole lot you can do to increase the brightness of when you're dealing in fluorescence. Another type of illumination methodology is some of the microscope slides that have the films on them can't use your phase contrast, which is one of the types of illumination or optics that I like. But one thing you can get, and Andy's going to demonstrate it, is differential interference contrast. This is just the optical method which creates a relief or a 3D effect, much like what you see with a scanning electron microscope. Y'all looked at the pictures and they have the animals, the little creatures in there, and they have all this nice little shape and structure and relief. Well, you can actually simulate that on a regular microscope, or a Brightfield microscope, or polarized light microscope, to give you that type of effect. Sometimes it's an aid in identifying spermatozoa. I always like to look for sperm with phase contrast. Even unstained with phase contrast is my favorite way of looking at it. But some of the slides now have this film in there, and that really affects the interference filters or the wavelength filters that you need in phase contrast. So differential interference contrast is a method of overcoming this. I wouldn't say this is the end-all be-all of sperm identification, but it's certainly a tool that you might consider, or a method you might consider on these microscopes to enhance your ability to examine unstained specimens. What happens when you have an interference with the interference as the sample goes through as the light goes through the sample, and then this is recombined at the objective, or this Wolfram prism at the top, and there you get this where they come together, and you have a modulation of your bright and dark areas, the grayscale versus your light, and it gives you this kind of a 3D effect, or this kind of a structure or relief effect of the sample. The image forms by differences in the optical paths caused by the specimen refractive index, or refracting the light, differences from the media. Basically, that's what we're looking at. That's how light's formed anyway. But this is a method of collecting the light and using it to show differences in the specimen. However, one thing you should note, some of these slides have architecture. In other words, they have little pores in them. As Andy will explain, they were designed for other applications, not forensics. And the other applications needed the little pores. Well, these little pores do give structure, and the differential interference contrast will enhance this structure in the slide, sometimes making it more difficult to identify objects there. However, there are some new slides, which I think this would be the second group that gets to see these slides in actual work. The basic concept of LMD, or laser microdissection, is, you've probably seen this. This is a Leica before. You have the laser coming down or coming up, depending on the microscope, and it cuts out a sample. It may either drop in there or it can be picked up by sticky caps. So that's the basic use of the, or there's no sense going out now. It's done.
You want to run it a second? Can you run it a second?
Let's see if I can.
All right.
Okay. Again, what we're doing is cutting out a sample from the slide and collecting it either from the top or the bottom, depending on your type of microscope. What most of the people, what you might want to say, okay, now how does that laser work? We're not going to go into great detail about how these lasers work. That's a little bit above this class. Fortunately, I have a good source about pulse laser, I don't want to say, mechanisms. My son has his PhD in physics, and he did his dissertation work on pulse lasers. So I can always call, okay, Jeff, how does this work? So he gave me a physicist explanation. He sent me some slides and said, okay, just explain this to the class. I said, I can't even explain it. You have to explain it to me. So what you're getting is a translated version of these pulse lasers. I called out what I semi-understood, and he gave me a little bit more explanation. But he does this work. He does basically works with pulse lasers. You know, he had a slide up there the other day I thought about. He does these lasers that do etching on stuff. And they were talking about, I think Kelly in one of hers has a sperm up there, and I think she made a comment like that. Well, there's no name on the sperm. I said, you know, my son, they have some labeling stuff. They probably could write the name on that sperm head. That wouldn't work, but it would be kind of neat. You know, you can have your sperm and have your case number, item number, stuff like that, labeled right on the sperm. Show it to the class. See, we can track the what do they call it? Chain of custody of this spermatozoa. We know where it's come from and where it is. And now we just put the name on there and say who it belongs to. Okay. Basically what happens with lasers is you pump up your electron energy in the atoms up to a level 4 or up to some levels. You immediately have a drop back down to a certain level. It almost goes up to the top and then kind of flops back down again. You then have a level drop from level 3 to level 2. And this is, again, quanta, so it's going to have a defined wavelength. Remember, there's not a continuum of energy levels in an atom. They go from like the D shell down to the P shell, or P's and F's and Q's. Y'all, not Q's, there's no Q. There's S, P, D, and F shells. And then they have, you know, they have all sorts of electrons that can go in there. Some of them have 10 electrons, 14, 6, 2, and stuff like that. Well, if it drops from one shell to another, it can only drop in certain energy levels. And those are defined energy levels. And that's where you get your defined wavelengths of lasers. So when it drops there, it emits a photon that comes out. And if it happens to be the right energy level, then it will have the right wavelength to where we can see it. Now, there are lasers that are invisible that you can't see. Now, if you look at this image here, you say, okay, that's a laser. But you know, that looks a lot like fluorescence, too. Remember I just explained fluorescence? You drop the electron up, drop down, leaves energy quanta. So what makes this different than fluorescence? First off, you do this in a cavity, usually a cavity surrounded by mirrors or a semi-mirror. This photon, then, as it's released, can knock another electron out of this higher energy level. And then that forms a photon. These photons have enough energy to start knocking these electrons out. Any of you ever do energy dispersive X-ray fluorescence? That's what you can do. You can use X-ray fluorescence to knock electrons out and identify elements. But in this case, we're using the photons to knock out these high energy electrons. Now, as these photons are formed, they're not absorbed when they hit another electron. So what happens? They start bouncing around there and start knocking out all these electrons. That's the stimulated part of light amplification by stimulated emission of radiation. So now we've stimulated this, and every time you knock out another photon, it creates a 2, then 4, then 8. That sounds like PCR, doesn't it? Exponential amplification, that's how I can relate to this. Okay, it's a chain reaction. Even goes back to nuclear chain reaction. But as you have the stimulated emission of radiation, they're bouncing back and forth in this cavity with these mirrors, knocking out more and more electrons. Now you've got the coherent beam. So that's where you get the laser. It took me years to understand that. My son had to explain it to me. But that's where you get your lasing. And if you have the mirrors, it bounces back and forth. But at some point, you have a semi-mirror and the laser or a half 50% transmission mirror so that it can come out from there. The neat thing about pulse lasers is that this is not a solid beam. You've probably seen the solid beam. You didn't watch Goldfinger, where they have James Bond laying up on the table and have that laser cutting across there. Well, these aren't a solid beam laser. They're actually pulse lasers where they have very short pulse lengths. 1 nanosecond pulses or 4 nanosecond pulses. I think we have a 4 nanosecond pulse laser. Then the new one is a 1 nanosecond pulse laser. Well, what happens if you get these ultra-fast pulse lasers? They work by multi-photon nonlinear process. In other words, they pump a lot of photons into the sample. These photons spread through there. They actually start ripping off or tearing out the electrons. But they do it so fast, these pulses are so fast that the molecule doesn't even have time to vibrate anymore. You know, remember in chemistry they talked about how the electrons are vibrating and they're translating and they're rotating and stuff like this. Well, the vibration is about a 0.5 nanosecond vibration. That's what your crystal electrons will vibrate at. We have pulse lasers that are faster than that. Unfortunately, these are not. But if you can get down to the pulse laser, it drops all that information or all that energy into the sample very quickly, and then it's gone. But the energy, because of the ability to keep hitting it with that energy, it transfers a lot of energy in there, but it doesn't have time for the heat to dissipate or dissipate very far. So if you look at your ultra-fast lasers, you get a nice clean cut like this. It goes in there, and the energy is so quick and so fast, it simply strips off all the electrons. You have plasma, and it ablates the sample. Nice clean cut, no recasting, no stuff hanging on the outside. Unfortunately, the 1 nanosecond and 4 nanosecond lasers leave a little bit of material like this. This is recasting and debris, where it actually initially does a slight melting, and before the pulse is even over, it has evaporated or evaporated all the electrons, causing it plasma. But it does have a slight melting effect and then goes into creating plasma, which basically evaporates the atoms in the area. So this is the type of cuts that you're going to be seeing with these 1 and 4 nanosecond lasers. Or today it's a 1 nanosecond laser. Here's the another cartoon of it, and you see the pulses there, where a nanosecond laser pulse first heats the target, then melts it, vaporizes it, and it does all that basically within one pulse. So you say, well, oh gosh, it is melting it. Well, it doesn't even have time for the heat to radiate to any significant amount. It's so fast. This is basically in 1 nanosecond. It has heated, melted, and evaporated the material. So again, the HAZ is your heat affected zone. Is really, in what we're going to do is there's not enough heat affected zone to really cause any damage to the sample. Yes, you can get too close to it, but it really doesn't have that much effect on it. The picosecond laser, and you can see in that, it doesn't have any of this heat affected zone. It goes in there and it doesn't do the melt or heat melt step. It just goes directly to plasma and evaporates it. Now, unfortunately, the lasers aren't at this stage right now. But then again, because we're dealing with a plastic substance, these lasers go through there fairly easily, and they're absorbed in the plastic substance, and they will ablate that. You say, okay, why doesn't it do it to the glass? Because we actually run the lasers through the glass. At these wavelengths, glass is non-absorbent to the light. If we went to a more UV laser, one closer down to 250 nanometers, it would take out the glass. But because the glass in the slides is not being absorbed or is very translucent to the laser, you're not having the same ablative effect or cutting effect on the glass itself, only on the plastic or the film in there. Advantages of fast pulse lasers. I've kind of gone over this. The fast pulse laser, 1 to 4 nanoseconds, it is greater than heat diffusion time in a molecules or in a substance, which is about 0.5 nanoseconds. It's not a whole lot greater than that, but it's just a point that it is a little bit slower, so it is going to have more of a cut, more of a melt and a cut, which may be an advantage since you are dealing with a plastic film. Material briefly melts, then energy strips away, electrons away from the molecules, forming a plasma. Basically, you're evaporating the electrons. Nearly all of the energy of the pulse is used in plasma formation, not heating the surrounding temperature. That's why we can do this cutting around there and have confidence that the heat of the cutting is not going to be affecting the sample. Little debris or recast material, yes, there's going to be a little bit of it. Little collateral damage to surrounding area. That's basically due to the beauty of the material, of the pulse laser. You couldn't do that same type of cutting with a long pulse or a solid cutting laser or a solid beam. That's what the plasma is. You can actually do a very short pulse. That 1 nanosecond is the length of the pulse. Now, how many of that times occurs a second is the hertz, or the number of cycles per second. I think 30 to 80 pulses per second is what we're seeing now, is what some of the lasers do. Depends on the type of laser and that you have. The history of laser microdissection is fairly new. It really started about, I guess, about 1996. It was basically in the medical field where they were looking at cancer studies. What was really happening, what was a concern then, not so much concern, but the reality was that cancer cells, you get tumors, but you also get a lot of, in some cases you get tumors where a lot of normal cells are incorporated into the tumor. So when you take a biopsy of a substance, you can look at a tumor cell. Here's your tumor cells group here. Here's your other cells all around it or intermeshed with each other. So and if you don't do any typing or genetic work on that, you simply have to take the amalgam or the grouping of the whole area. If you take the tissue culture, you cut it up, and what you get is both types of cells. By going to laser microdissection, you might be able to tweeze out or cut out individual types of cells in there. Say, okay, here's a clump of cancer cells. I can cut them out and do the genetic analysis on them individually. One of the things they look for in cancer cells is heterozygosity loss. Or was it LOH, loss of heterozygosity? And they want to look at the genetics. Because these cells are dividing so fast, they're starting to slough off chromosomes. So that was one way of looking at the individual cells in a cancer biopsy or a cancer slice or something like that. So that's where it really got started. Next was been about when Christine started using it. That was about 2003, 2004, when they got their microscope and started using it to say, hey, this is a good idea to excise individual sperm or epithelial cells. And so that's where it started from there. The history of that in the American Academy meeting of Forensic Sciences in 2004, that was the first incidence of use in for spermatozoa, separating spermatozoa, the sperm DNA from the epithelial cell DNA. I think, I don't have it listed on here, but in 2006, work in our laboratory did her master's thesis on the ability to separate male and female diploid cells. And that might be another bit of the history there. We've actually accomplished that, where you can take male and female diploid cells, like what you might see in a breast swab or a bite mark swab or fingernail scrapings, and be able to say, okay, here's the female cells, here's the male cells, we'll separate them, just as you can separate the spermatozoa from the epithelial cell. Types of LMD microscopes. We have the Leica microscope. You're going to see that all week, or see all week, all 2 days, today and tomorrow. So you're going to learn a lot more about it. And I've got some information here. I'm not familiar with all different types of microscopes, just a couple of them. And then Christine is going to talk about more, or if you have any other microscopes in here we'd like to discuss, we can kind of give you a I don't want to say an education on, but we certainly discuss the pluses and minuses of them. The Leica is an automated microscope. You don't have to deal with coarse and fine focusing anymore. It's got the little mouse that you can focus on there, change your light source, change your sample orientation or location. Brightfield fluorescence has alternative optics. It's got phase contrast and DSC if you want to use those. We very seldom use anything but the Brightfield and fluorescence. Slides, all the slides have a film coating. We have the pen slides and we have the new director slides, but they all have a coating. You cut the coat off, or at least in the pen slides you cut the coat off. The other ones are energy transfer slides to where you can knock the sample off. The laser cuts the plastic film, which allows the cut sample to drop into a tube, and you can put up to 4 different samples can be placed on the stage, but I think there are some other holders where you can put more samples under there. The UV laser does the cutting. The new diode laser has a wavelength of about 355 nanometers, 80 hertz. I think that's right, 80 hertz. The older one, which actually we have the older Leica microscope, and I think Christine does also. What she worked with was the older one. This one has the lambda wavelength of 337 nanometers. It's a gas laser, and it works at 30 hertz. The laser beam is directed through the objective by prisms. This is kind of a novel. Most of the other ones have a fixed laser, and you move the stage. But in this one, the laser, as you showed through the picture, was a Leica promotional video that you saw earlier, although I just wanted to use it to show you how laser microdissection works. The lasers actually focus through the objective. One of the things that might give you an advantage for is, as it goes through the objective, that affects the spot of the laser, the size of the spot. So as you go into the more or the higher magnification objectives, you actually get a finer beam, I believe. Laser capture microscope. Here's your MMI microscope, the cell cut. This is one sample collected on a sticky cap. And then, of course, once you have it on a sticky cap, you then have to take the sample off of there or do the digestion, digest the sample off of that. Samples can be easily expected after cutting. That's one of the advantages that they say with this microscope is once you've made your cuts, you can then examine the cap and see how many cuts you've had on or how many samples that are on there. Pulse lasers cutting by moving the stage, and they propose that this is a method is contamination free. To be truthful, all the microscopes say, hey, this is contamination free, but again, that they put a big point on that their method of cutting and collecting is contamination free. Up here is kind of a picture of how this occurs, and you can see the sticky cap where the samples are collected. Christine has a little bit more information about the other microscopes, more so than I, and your Arcturus and the Palm microscopes. I'm going to let her discuss those, or just for a moment.
Yeah. Unfortunately, we don't have slides on that. And later, I'll give you actually an Excel spreadsheet kind of comparing some of the differences between the instruments. But the two that Pat didn't mention, one is the Palm system, which several of you have or are getting. The real difference on the Palm system is that you're cutting from the membrane, but you're also catapulting it up. Instead of using what the Leica system is using the gravity to collect the sample in a tube below, the Palm system is catapulting the sample up into a tube. And then the other system, the Arcturus, which now has the new version, is, what is the Veritas? Yeah. That uses basically a normal glass slide is where your sample is prepped on. And it uses a special cap that holds a membrane. And it comes down on the sample and kind of basically melts the membrane onto your sample and pulls your sample up. So those are kind of the different ones. And we can actually discuss a little bit more, especially since some of you have these instruments. And when I hand out that spreadsheet, perhaps we can talk about the differences, because most of our experiences are with the Leica.